this is Mrs. Roropaw. We're going to give this video one more try. So it's just I'm just going to talk a little bit about batteries and help you diagram them. This is the helper video that goes with batteries, which are voltage sources in a circuit. The objective today is students will copy diagrams of how batteries work. So the diagrams are in your text, and then I'm going to challenge you to try to draw a diagram of a lemon battery, which is one of the most misunderstood labs that you see out there. A lot of the explanations for the lemon battery are not even related to the lemon battery. So I think by the end of today, you should have some idea of how a lemon battery works. And so I'm going to challenge you to draw that diagram after you've drawn these others. So you read a little bit about the history of the battery and how it was invented a long time ago, several hundred years ago. And it was one of the first electrical devices that actually worked, that could do anything. And what Volta used to do, he didn't really do anything with it. He would just kind of touch it to his tongue and say, ooh, it's electrical. But he didn't actually do a whole lot with it. But a few people after him immediately put it to good use, separating. With electricity, you can separate elements that are not easy to separate any other way. And so one of the first contributions of the battery was to the field of chemistry. So if you've had chemistry before, some of this is going to be review, but I know that many of you haven't. And so I need to go over this before we go on to talk about circuits. So when we have a circuit, I'm going to put something in the circuit. Let's put a light bulb in the circuit. All right, so let's see, I want to power this light bulb with my circuit. And I can't just hook a wire to the light bulb and have it go. Like, that's not going to work. But it turns out that I can, let's see what I got here. I've linked a video. A fella takes a beaker of acid, sticks 2 pieces of metal in it, and lights a light bulb with that. And it's super cool. It's the simplest kind of battery. And what I was a little disappointed though, because what he didn't show is how quickly that battery runs out. When you just use the same beaker and the 2 pieces of metal, the battery lasts seconds. And that video, which I've linked that you can see, makes it seem like the battery stays lit for a long time. The chemistry of batteries, making them work, making them deliver a lot of power, and making them deliver a lot of power for a long time is exceedingly complex. It's not a simple thing. And so that video makes it look like it's simple. But we are going to start with something almost that simple in our diagram. So what that battery does is, without any other electric source, it provides a separation of charge. So I'm going to have a plus charge on one side of my battery and a negative charge on the other. And this is the symbol for battery that you're going to use. So a battery is a voltage source. And the way that provides energy to the light bulb, and this is just review, is it establishes an electric field along the wire that then causes the electrons in the wire to move. And that movement through the filament is what lights the bulb. But in order to establish that electric field, you need to have a charge separation in the battery. So a battery provides, a voltage source provides a charge separation, which is what we call, and that means it's a voltage. Okay? When we separate charge, we have a voltage. All right, but how does a battery do that? Well, a battery uses chemical energy to do that. So energy doesn't get created or destroyed. It just gets changed around. So the battery seems to create electrical energy, but what it really does is takes energy from chemicals or from metals and releases that energy slowly, delivering it to the light. And how does a battery do that? We are going to discover that today. But first, you make sure you understand that the battery is a voltage source. It provides a charge separation. It does not create energy. It simply converts chemical energy to electrical energy. So it provides a charge separation, and it converts chemical energy to electrical energy. And it does it in an exceedingly portable and convenient way. So they are super cool, but they don't create energy. Okay, they simply convert it. Okay, so I'm going to erase this and then we'll get on with the diagram of the battery. Okay, so how does a battery convert chemical energy? So how does a battery convert chemical energy to electrical energy? This is how. So the first diagram that you're going to copy, you have the number for the one you have to do, shows this. It's got an electrode here. I'm going to tell you what each of these things are, and then I'm also going to write them down. And it has an electrode here. And this is that really simple battery with one caveat, and I'll explain in a second. And then it's got acid. Okay, so this is, I think it's sulfuric acid. And this is a carbon electrode. And this one is a zinc electrode. So that's what it's made out of. Basically, it's a beaker of sulfuric acid with a carbon on one side and zinc on the other. And if you connect a wire, okay, you can light a bulb. Woo! And I'll just show that here. I'm not connecting my wire very well. Whoops, there's my bulb. Woo! I'm lit, okay? So I can light a bulb. So this is a battery. It converts chemical energy into electrical energy, and it's exceedingly simple. So let's diagram it and see how it works. So for the labels, I'm going to use a different color. Zinc is there's electrons coming out here. So the electrons are going that way. So the zinc provides those electrons by a chemical reaction that goes on right here. And that chemical half reaction looks like this. Zinc solid goes to zinc cation plus 2 electrons. Now, the electrons obviously go down the wire, and we'll talk about why that is in a minute. And this is the zinc solid, right? This is the solid. And the zinc 2 plus ends up in solution around this electrode. Now, this whole dealie here, this whole thing here is the electrode. And this one is the negative electrode. This part here is the terminal. Okay, so although electrons are going this way, as we learned yesterday, current, as defined by the positive charge direction, is going this way. Now, what's very interesting, okay, so we've got positive charges here floating around this electrode, a negative electrode. We've got a negative terminal here. And then conversely, on the other side, we're going to have a positive terminal. And hopefully you guys are keeping up and writing this down. This whole thing here is the positive electrode. And there's we use some different words for these when we're talking about electrodes. The electrodes this one's called the anode, and this one is called the cathode. Okay, so now you notice I didn't draw anything around the carbon electrode. That's because the carbon does not react in and of itself with the sulfuric acid. So the zinc does react, carbon does not. Instead, what reacts is the water itself, the acid itself. So an acid has hydrogen atoms without electrons. That's what defines an acid, is that it's got a lot of what we call protons floating around in solution. And so here at this electrode, what's happening is we have 2 protons interact with 2 electrons. Where do those electrons come from? From the wire, okay? So the electrons here are coming in on the wire. So if you deliver electrons here, the carbon can conduct the electrons down into the solution, and there's hydrogens here floating around, and they interact with the carbon, the electrons coming down the carbon, to make 2 molecules, one molecule of hydrogen gas, okay? So this is a gas. All right, and this, a lot of times you'll see a little AQ here, and that means it's aqueous, which means that it's dissolved. So you've got dissolved zinc, you've got hydrogen gas forming, some of it which is dissolved, and some of it just escapes from the battery usually. And that is how the electrons go from zinc through the circuit and then out the other side. If we stopped the electrons going out the other side, we would also stop the current and the light bulb would go out. Okay, we have to have this circuit, we have to have electrons moving through the circuit all the time. The electrons have to move in order to power the device. Okay, so I think I've got the positive and negative terminals, the positive and negative electrodes. We've got the half reaction here. We've got a half reaction here. When they say half reaction, that means they're not really telling you what happens to the electrons. They just go down the wire, and they're not really in here. They just say electrons come from somewhere, and that's why this is a half reaction instead of a whole reaction. Okay, the last thing I didn't talk about yet is the electrolyte. So in order for this to keep going, you need something here, the electrolyte, that can take away and deliver positive and negative charges. And that's what this is right here. In this simple model of a battery, that electrolyte is the sulfuric acid. It's a liquid. But in this model here of a battery, this is usually a paste. And so it's got different metals in it that make it able to transport those electrons very well. And in this case, they also have to accept the electrons just as the sulfuric acid does here. So why do batteries wear out? Well, you'll notice this zinc is always dissolving. And so here I've got some zinc in a beaker in some acid, and I left it there overnight. And you can see what initially started out as one single plate of zinc is now 2 chunks with a whole bunch of zinc floating around in solution. Eventually, this zinc will dissolve completely, and then the battery will be dead. It won't work anymore. Okay, so I think you guys can go ahead. Well, no, I better draw the next one too. So let's do that. Let's talk a little bit about how this battery works, which is different. Instead of being a liquid, we're going to have, let me see how much of my board I can see here. We're going to put it here. Okay, so now we're going to diagram this battery, which is the kind of battery you use all the time. And I'm going to show what's inside. So here is the positive terminal. And in this case, there's a hole, and the bottom is the negative terminal. And the way they do this is by, you'll see that inside the cathode is a cup. Okay, so it's a cathode cup. So the electrode is a cup. So this is an electrode cup. The electrode is shaped like a cylinder with the hole at the top. And this terminal connects to an electrode that goes all the way down like that. So the negative terminal is just the bottom of this cup, and there are insulators on each side like that. So the only part of the cathode that sticks out is right here at the bottom, okay, because the insulators hide the cathode cup from the sides. And this is the positive electrode. Did I do this wrong? Hold on. I think I've got them the wrong way. Negative terminal. Yeah, that's right. This is the positive electrode, and this is the negative electrode. So negative electrode cup, because it's made out of zinc. and this is the positive electrode here, and this is made out of carbon. Okay, so you got this positive electrode here and a negative electrode cup made out of zinc. So I've got negative terminal, negative electrode, positive electrode. Which parts did I leave out? I think that only leaves, oh yeah, the electrolyte. This is an electrolyte paste. So even though it's really similar to this simple sulfuric acid battery, but instead we've got a central electrode, a cup-shaped electrode, and then a paste around it. And then the half reactions are going to be the same as the ones that are right there. Close enough. Anyway, we're not going to go into all the details of the chemistry of batteries. So I think you guys have enough information to diagram how a lemon battery would work. Remember, lemons are filled with citric acid. That's a clue. I want you to look at the video on lemon batteries, and I want you to draw a diagram. There are so many terrible videos on lemon batteries, but look at some of them. I encourage you to do that. I attached a copy of the best one I could find, but it doesn't have a diagram of the half reactions. So I think you guys can do a better job, and I want you to try to do that. I think that's it. I know I've talked a long time, so I'm going to quit. If you have any questions, let me know. Otherwise, good luck.